Hello, hi. Welcome to lecture number 3 of the first week of this course on programming and data structures offered by NPTEL. So, to answer some of your questions on the forum in a brief manner, many of you are very concerned about the activities and the weightage for the activities. The course is going to be designed in such a way that the activities are for you to assess how well you've learned the material, and some of these activities will also challenge you in the sense that they will involve you to meticulously perform a certain amount of work after understanding the question. For example, if you recall uh, the insertion sort comparison question, many of you actually attempted to count the number of comparisons made by the algorithm insertion sort, whereas the question very clearly stated that you should count the total number of comparisons made by the function insertion sort. So these are the subtle things that you should make a note of when you perform these activities. At the end of this lecture, you will also notice that the first programming assignment would have been released, and the details of the deadline, submission deadline for this programming assignment will also be made available to you at the course webpage itself. The other class of questions have to do with pointers uniformly. Many of you have questions about the connection between pointers and arrays, and why in scanf ampersand is there and ampersand is not there. The best way to sort these questions is to simply write a small program. Right? Here is a small recommendation for such a program. Define an array and read elements into the array using scanf. Right? Now what you try and do is make the mistakes, compile, run, and see what kind of error messages you get and what kind of warning messages you get during compilation. This is the best way to actually understand, of course, along with a standard textbook that will help you, which will standard textbook which will guide you through your efforts, right? So understand that universally when you read something using scanf, the format specifier tells you what data type is going to be read from the input. Now the question is, where should you store the value that has been read, right? And that information is given as a second argument to scanf. The first argument is a format specifier. The second argument tells you where to store that value. Now, if you think of it this way, understand that it's an address. Okay? And then if you think of the name of an array is actually a pointer, then it already is an address and therefore you don't need an ampersand. So work these details out and things would become clear. The best way is to actually write a small piece of code rather than post on the forum and try to elicit answers. I hope most of you, when you post on the forum, you've already tried to experiment with a small piece of code before you post on the forum. And today's lecture, we move one more step towards studying data structures. We we study the concept of recursion, and recursion is extremely important because many methods that you write now uh, when you design a data structure, recall designing a data structure is to define an appropriate data type and talk about how, or write functions which will tell you how this data structure is going to grow and shrink. Many of these functions are best specified as recursive functions. Therefore, a certain level or a significant level of familiarity with recursion is extremely important. And in today's lecture, we will look at simple recursively specified functions. Then we will see a program in which the function definition is recursive, and we will see how it works. So today's lecture is likely to be relatively shorter than the previous lectures. Okay, so now let's go to the slides for today's lecture. Alright, so today's lecture is about recursion. It's a third lecture in the first week of this course. So let us just quickly get past the definition of a recursive function. So a recursive function is first of all a function, and it is called recursive because from the body of the function definition, a function call is made. So such a function is a recursive function. Now, why is this an important concept? Recursion itself is very important because many mathematical functions are specified naturally using recursion. Understand the distinction between the usage of the word recursion as a recursive function in a programming language against the specification of a mathematical function using recursion. So, and again observe that the word function means two different things in two different contexts. When I say mathematical function, I mean a function as we studied in school. It's a function with a domain and a range, etc., etc. So do not get confused with, or do not miss making the distinction between a function call, the definition of a function, and the mathematical function. So these are all three different concepts, and ensure the three different concepts, though they use the same words, right, do not overlap in your mind. This is extremely important. So now let us look at the factorial function. The factorial function is a mathematical function. Now, because it is a mathematical function, it is useful for me to tell you what the domain of the factorial function is and what the range of the factorial function is. The domain of the factorial function is a set of positive integers. And the range of the factorial function is also the set of positive integers. Therefore, let us look at the simplest values of factorial. And let us even recall what factorial is. Factorial of 0 is 1. Factorial of 1 is 1. Factorial of 2 is 2 multiplied by 1, which is 2. Factorial of 3 is 3 multiplied by 2 multiplied by 1, which is 6. In general, factorial of n is n multiplied by the factorial of n minus 1 if n is greater than or equal to 1. If n is equal to 0, then factorial of 0 is given as a fact. Right? It is the base case. Right? Factorial of 0 is given as a fact. It is not recursively specified. It's given as a fact, and factorial of 0 is taken to be 1. Now, such a definition of a mathematical function is called a recursive function. If you go back to your school mathematics, you will find that the greatest common divisor of two integers also has a recursive specification. Right? Similarly, if you look at the binomial coefficients, they have recursive specifications, and so on and so forth. There are many mathematical functions which are recursively specified. Now let us come to the world of programming languages, and in particular programming language C. C supports programmers writing recursive functions. Using recursive functions, mathematical functions which are recursively specified can very easily be converted into computer programs. I repeat this. The world of mathematics gives you many recursive functions. C allows you to define recursive functions. That is, it allows you to define functions. From the body of those functions, you can make a call to the function itself. So these are recursive functions in the C programming language. Therefore, the mathematical functions which are recursively specified can be very easily converted into computer programs using the power of recursion provided by programming languages, in particular the power of recursion provided by the C programming language. So this is why recursion is extremely important. Many things which are mathematically specified, many mathematical functions which are recursively specified can immediately be converted into computer programs. So keep your eyes open for mathematical primitives that you study either at school or college, and see which of them are recursively specified, and if you see something is recursively specified, immediately you can do this exercise of converting it into a computer program using the facility or the feature of defining recursive functions. So let us just look at a crisp recursive program for factorial. So let us just recall one thing. A recursive program has to have well-defined exit conditions. If you don't define well-defined exit conditions, then a recursive program will run forever and exhaust your system's memory before it stops. Or rather, it exhausts the amount of memory that your program has access to before the program will stop executing. And remember that this is not an infinite loop. I'm not going to go into the details of what happens when a recursive program runs forever, but I just want to tell you that when a recursive program, a poorly written recursive program that does not terminate, is not an infinite loop. It is different from an infinite loop. An infinite loop, essentially the CPU keeps running forever and will literally not terminate till certain boundary conditions and index conditions are met. On the other hand, a recursive program which is poorly written will terminate because it will run out of a certain kind of memory that your program has access to while execution. Okay. So what is the most important thing that I've said so far? That you have to have very well defined clear exit conditions in your recursive function definition. So now let us look at this recursive function definition. A parenthesis is missing. There's a small error here, but it doesn't matter. Let us just look at the definition of the function called fact. Fact takes as an input argument an integer n. It returns an integer, right, as specified here. It says that if n is equal to 1, it returns the value 1. Otherwise, it returns the value n multiplied by fact of n minus 1. There must have been a parenthesis here, and that has been missed. This basically encodes the mathematical definition of the factorial function, saying the fact of n is n multiplied by fact of n minus 1. One must understand how a recursive program executes, and that is the focus of today's lecture. However, as you can see, once one understands how recursive functions are evaluated at runtime, a recursive program is often simpler to understand. But it's very important, you must get used to the concept of how recursive functions are evaluated at runtime. And typically, recursive programs also use a smaller number of variables, though this is not something that we will dwell upon. There is another kind of recursion which we call tree recursion. It doesn't matter why it is called tree recursion. It is a concept that you will become clear with as we go through this course. When a recursive call is made more than once inside the function, then one potentially gets a special kind of recursion that is best represented using a nonlinear data structure. I repeat this, certain mathematical functions are specified recursively using the values of the same function on more than one smaller value. I repeat, certain mathematical functions are specified recursively using the values of the function on more than one smaller value, as opposed to factorial. Factorial just depends upon n, the factorial of n minus 1. Factorial of n depends upon n multiplied by factorial of n minus 1. So factorial of n really depends upon factorial of n minus 1. On the other hand, let us look at the Fibonacci numbers, which are specified by the following recurrence equation. This is a mathematical function. I'm sure all of you are familiar with the Fibonacci sequence. The numbers in the sequence are called Fibonacci numbers, or Fibonacci numbers. And if n is 0 or 1, so this is the example of tree recursion where a recursive call is made more than once. So in the mathematical definition of the Fibonacci numbers, the nth Fibonacci number is a sum of the previous two Fibonacci, immediately previous two Fibonacci numbers, and the base values of the Fibonacci numbers for n is equal to 0 and 1 are 0 and 1 respectively. All right, so these are examples of tree recursion. And similarly, here is the Ackermann's function, which is another recursively specified function. It's one of the fastest growing functions. I'll encourage you to actually plot the values of these functions using an Excel spreadsheet. You can actually do this manually for different values of m and n to get an understanding of how fast the Ackermann function actually grows. So this is a small repeat of the Fibonacci function specification in the C programming language. Again, the flower brackets are missing. It says observe that there are two ifs, right, which very clearly specify the return conditions. If the argument n is equal to 0, then you return a value 0, and if it is equal to 1, then you return a value 1. Otherwise, you return the sum of the Fibonacci number n minus 1 plus Fibonacci number n minus 2, which is now recursively calculated. And just after this, the parenthesis should have been there. Let's visualize this as a tree-like structure, and let us look at the fifth Fibonacci number. The fifth Fibonacci number is the sum of the previous two Fibonacci numbers. It's a fourth Fibonacci number and the third Fibonacci number, which in turn is a sum of the third Fibonacci number and the second Fibonacci number. And the third Fibonacci number is the sum of the second Fibonacci number and the first Fibonacci number. And the third Fibonacci number again here is the sum of the second and the first. The second Fibonacci number is the sum of the first Fibonacci number and the zeroth Fibonacci number, and so on. So as you can see, there is this very nice full binary tree structure. So by full binary tree, I mean that for every node, there are exactly 2 children except for the leaves which have 0 children. So for example, this node has exactly 2 children, and this node has no children at all. It is a leaf node. And observe that at these leaf nodes, you get the base value. That is Fibonacci number. The 0th Fibonacci number has a value 0. The first Fibonacci number has a value 1. And these two values are added, and this is the value of the parent Fibonacci number, which is the second Fibonacci number, and so on. You can see that the fifth Fibonacci number has the value 5. So therefore, observe that the evaluation of the Fibonacci number recursively is same as evaluating a tree-like structure where the leaf nodes has some values, and these values are propagated upwards towards the root of this tree. And this is an example of a function which is evaluated by visualizing it as a tree. And this is what I mean by saying that certain mathematical functions are viewed in the world of tree recursion. Now let's come to the programming exercise of the day, and it is a very famous puzzle, and there are two things here. In the rest of the lecture, I'm going to try and show you how to think recursively and how to also program recursively, or how to program recursive functions. So let us just study the towers of Hanoi puzzle, right, for a short time. So in this puzzle, there are three vertical rods. I call these rods A, B, and C. And there are a certain number of discs. Each of these discs has a different radius from the other discs, and each of these discs can slide into any of the rods. Now the exercise is the following. Initially, all the discs are arranged in a stack in ascending order of size in the rod A or the tower A. This is the first tower, right? And all the discs are arranged in a stack-like fashion, right? One on top of the other, with the smallest disk at the top and the largest disk at the bottom of the tower. So in other words, all these disks are arranged in a pyramid-like structure on one tower or one rod, and this rod, let us call it A. The goal of the puzzle is to move the whole pyramid to rod C, and one has to observe three rules which are listed below. At any step, only one disk can be moved, and only the disk at the top of a tower can be moved. That is, only the smallest disk can always be moved. That is, the smallest disk in any of the three towers can be moved. And at no point in this movement can a disk be placed on top of a smaller disk. So therefore, the condition that is placed on the movement is that at any point of time, if you stop and look at the snapshot of the three towers, what you see are pyramids whose sizes are decreasing from the bottom to the top. The disk sizes are decreasing from the bottom to the top, and this property must be satisfied at every point in the movement of the disks from tower A to tower C. So this is a puzzle, right? So any of you can pick up, the towers are not so important. You can get 3 disks or 4 disks or a certain number of disks, all of different radii, and place them on the floor and mark the towers using some chalk piece on the floor, and you can play this game. Right? So what is the solution to this puzzle? And secondly, can one write a program that can print out a solution to the puzzle? Therefore, there are 2 exercises here. Right? How does one solve the puzzle is one exercise, and the second exercise is how do you write a program to print out a solution to the puzzle. So let us deal with the first problem here. How does one solve the puzzle? I am sure each of us will attempt multiple things. This being a short lecture, I will actually directly try to inculcate a certain thought process in your mind. Okay? And I will try to put in the idea of thinking of recursive sub-problems. So that is the whole idea, right? So I'm going to try to suggest that you take the problem and see if you can solve the problem, if you know how to solve smaller sized problems. That is, let us assume that you want to solve the case of the problem when you have 3 disks in tower A. Now if you know how to move 2 disks, then can you solve the case of the problem when you have 3 disks? So this is the idea of recursive thinking. Right? So I repeat this again. You want to solve a problem of a certain size. You ask, can I solve the problem if I know how to solve instances of the problem of smaller size? So let us start off with the simplest case. Let us assume that you have only one disk. The disk is in tower A and you want to move it into tower C. Okay? It's very simple. Right? So I'm going to motivate you to think about a function called recursive solve. The first argument for recursive solve is a number of disks which are in the first tower. The tower is A, B is the intermediate tower, and C is the destination tower. I repeat. So in this recursive thinking thought process, I'm going to tell you to think about a recursive function called recursive solve. The first argument to this function is the total number of disks that you have. The second argument is the tower that contains these disks, that is in this case the tower A. C is the destination disk, that is you want to move all these disks into tower C from tower A, and you can use tower B as the intermediate tower. Okay. Now here when you have only one disk, the problem is very easy. You do not use tower B at all. Simply physically move A to C. Physically move is again a function, okay, which is always applied in the case when you have to move only one disk. Now if there are two disks, let us think of the problem recursively. Now you know how to solve the problem when you have exactly one disk to move. Now we have to solve the problem when you have two disks in tower A and you want to move it into tower C, and you are free to use intermediate tower B. How does one think of it? The way to think of it is to close your eyes and imagine that the biggest disk doesn't exist at all. Okay? So now what do? You recursively solve. You recursive solve, assuming that you are moving only one disk. Which disk? The topmost disk in tower A to tower B via tower C. Right? And we know that if you need to move only one disk, it is the base case. You simply move from the source to the destination. That's what we did here. Right? Whenever you have one disk, you move the disk from the source to the destination directly. Right? Similarly here, so there is only one disk, you want to move it from A to B via C, you just physically move it from A to B via C. Now the next step would be to move the disk in tower A. There is now only a single disk after this step, right? That is the largest disk. Now you move that largest disk from A to C via B, right? Because there is a single disk, it's a physical move directly from A to C. And the last step would be to remove the second disk, which is the smallest disk, which is now in tower B, to C, again directly from B to C. Therefore, we have performed three moves. Observe, very importantly, you wanted to solve the case when you have two disks, and observe that you have solved the problem three times. Okay? Solved a problem three times when there is only a single disk. Okay? So therefore, you have recursively solved the movement problem for two disks using three function calls to the movement problem when there is only a single disk. So now let's try and see how to do this when you have three disks. So what does recursive solve look like when you have to move three disks from the source tower A to the destination tower C via B? Okay, the idea is very simple. Okay? You recursively solve the problem assuming that there are only two disks. Okay? That is, ignore the fact that the third disk is at the bottom of tower A, it is the biggest disk, ignore it. Imagine that you are moving only two disks, the top two disks from A to B via C. Okay? So this is a black box recursive call, don't worry about how it works. Okay? You know how to do it from here. Okay? So now you recursively solve the case when you have two disks to move from A, move it to B via C. Right? So therefore, A is now considered as the source tower, B is the destination tower, and C is the intermediate tower. Observe that this is a recursive step. So this is one of the steps that you perform to solve the problem when you have three disks to move, where the source is A, C is the destination, and B is the intermediate thing. To solve this, first you say, I'm going to think of A as a source, B as a destination, and C as the intermediate tower, and I'm going to move only the top two blocks which are in tower A, or the top two disks which are in tower A. Let us assume this has been successfully done. Now what do you see in tower A? There is only one block. Okay? You move it all the way to C. Okay? So that is a physical move. This is a base case, move A to C directly. Now you have your two blocks in B, you want to move them to C, and you move them via A. So your source now becomes B, your destination becomes C, which is the final destination in any case, and you move it via A, right? And you solve the sub problem of the in by considering the case where there are only two blocks. Right? As you can see, recursive solve on two blocks takes three moves. That's what we have seen here. Recursive solve, when you have only one block or one disk, takes only one move, and then a recursive solve on two blocks or two disks takes another three moves, a total of seven moves. Right? So that is 2 power 3 minus 1. So we just generalize this to 4 moves and 4 disks and n moves. So if there are 4 disks, recursive solve wants to solve 4 disks from A to C via B. I hope this is clear now. Okay, first step, do recursive solve for the top 3 disks in A, from A to B, the intermediate block, intermediate tower via C. This will take 7 moves. That's what we studied in the previous slide. Then you move the bottommost disk, which is now in tower A. It is completely exposed because everything has been moved to tower B, and you move it to C. That's a physical move, and that is described as a recursive function call. Right? Of course, B doesn't get used here. Right? Okay. And then you now make B as your source. Right? So the remaining 3 disks are now in B. Right? You move them to C via A, which is now empty. Right? And that takes another 7 moves. And I'm sure you can very easily generalize this to the case when you want to move n disks from A to C, right, via B. Right. So let us just understand the whole thing again. Right? It's extremely important for you to understand that you have not yet found the sequence of moves. You only recursively said that the sequence of steps that are required to move n disks from tower A to tower C can be obtained by recursively finding the sequence of steps to move n-1 disk from A to B via C, then by performing this single physical move of the largest disk from A to C, and then recursively moving the disks from B, the n-1 disks from B to C via A. Observe that to be able to find the sequence of moves for every n, you will have to write down this recursion tree that we spoke about. This is also going to be a binary tree. Okay? And if you list down the leaf nodes in an appropriate order, you will essentially get the whole sequence of moves that need to be performed to achieve our goal of moving n disks from the tower A to tower C. This is what our program is going to do. And what is the most important thing? Right? So the role of source, intermediate and destination towers are repeatedly changed in a certain simple manner in the description of our recursive algorithm or the recursive function. Right? So now let us go to the C program and let us look at one execution, and this will finish today's lecture. Alright, as you can see, I have already tried running this program a couple of times. Alright. So from the previous lecture, you will notice that I have removed stdlib.h and string.h. It is unnecessary for us to include these preprocessor directives. All that I need is simple printf and scanf functions which are available in this header file stdio.h. Okay. So this is a very simple program to solve the towers of Hanoi problem. The input is a single integer n and the output is a sequence of moves. Right? Now, what is the sequence of moves? Every move, right, is essentially one of these 6 possibilities. This one says move from tower 1 to tower 2. Which one do you move? Only whatever is at the top of the tower. And where do you move it in tower 2? To the top of tower 2. Then this one says move from tower 1 to tower 3, tower 2 to tower 1, tower 2 to tower 3, 3 to 1 and 3 to 2. Therefore, one has to output a sequence of moves. Each move is from this set and each move specifies from which tower to which tower you move a disk. And if you follow the output, this output sequence one after the other, right, that is output by this program, one moves the whole tower of n disks from tower 1 to tower 3, satisfying all the conditions that are outlined in the towers of Hanoi problem. This is the function prototype. The function prototype has 4 integer arguments. Right? The first integer argument, as you will see, is for the number of disks which are there. The second integer tells you the tower number. So does the third one, and the fourth integer argument tells you which are the tower numbers. And in this program, we assume that the towers are numbered 1 to 3. 1, 2 and 3 are the tower numbers. So here is the main function. Okay. Number of disks is the integer variable. We read the number of disks that we want to solve the problem with. Right? And this is the number of disks and not the number of keys from a previous program. And here is the function call. Okay. So the function is called tower of Hanoi. The first argument is a total number of disks which you want to move from H1, which is the source tower, to the destination tower 3 via the intermediate tower 2. Finally, you return 0 on successful completion. Alright, so now let's look at the recursive function. Okay. It follows the same template of what we discussed when we looked at the slides, okay, except that we have strategically put in appropriate print statements. Okay. So let us just look at the sequence. If the number of disks is 1, what do? We perform a move. Right? Okay, where do we move from? We move from source to destination directly. Therefore, that is what this print says. Then one makes a recursive call. If the number is more than 1. Right? So you move from source to destination and then you return to the place from where the function call was made. Okay? If number is equal to 1. So the control will reach this statement if the number is actually more than 1. Right? If number is more than 1, then there are at least 2 blocks. So you solve the tower of Hanoi problem on 2 blocks, moving them from source to intermediate. That is, you move the 2 blocks from source to intermediate via destination. Okay? Observe that this is a recursive function call. Now, once the execution of this function is completed and the control has returned, okay, to this point, okay, let us look at the property that is satisfied. The top n-1 disks have now been moved from source to intermediate, and the source has only the largest disk and the destination is empty. This is a property, right, after executing this function. Now, the source has only one disk, so we move this directly from source to destination. At this point, the destination has the largest disk, the source is empty, and the n-1 disks are in the intermediate tower, and they should be moved to the destination tower. How is this achieved? This is achieved by making a recursive function called the same function, saying that you want to move these many number minus 1 number of disks from the intermediate tower to the destination tower via the source tower. Okay. And once this is done, okay, at the topmost level of recursion, okay, you can return and all the towers would have been moved from source to destination via intermediate, and it is quite clear that because each of the moves is always moving an object from the topmost disk, always moving a disk from the top of one tower to the top of another tower. and it is easy to observe that the conditions are satisfied. So the best way to observe this, instead of writing a formal proof, which we would do if we were doing an algorithms course, is to actually test this program. So let us just compile and run this program. So this expects an integer, and let us assume that I give only one disk. Then it says move 1 to 3 directly, which is fine. Now let's say there are two disks, and before I hit return, let us just verbalize the plan. And let us just state the plan. So the idea would be that there are two disks in tower 1 and they all need to be moved to tower 3. So the idea would be to move the topmost disk to the second tower, then move the bottommost disk to the third tower, and then move the single disk, which is the smallest one, which is now in the second tower, to the third tower. That is, the plan would be 1 to 2, 1 to 3, and then 2 to 3. Let us check if this is right. Right, 1 to 2, 1 to 3, and 2 to 3. I'd encourage you to use a notebook and test, check whether this is right. So let's run the program for 3 and then stop. Right, so let us just take a look at this. You want to move 3 disks from the first tower to the third tower. So what we do is you first take the first disk and move it to the third tower. Okay. This is the topmost disk. Then we move the second disk in tower 1 to tower 2. Then you move the topmost disk, which is now in tower 3, the smallest disk which is in tower 3, to tower 2. At this point of time, observe that the top two disks which were there in tower 1 have now moved to 2, which is the intermediate tower. Now you move the disk from the largest disk from tower 1 to tower 3, and now you move the two disks from tower 2 to tower 3 via 1 as an intermediate tower. So you move the smallest disk from tower 2 to tower 1, then the second smallest disk directly goes from tower 2 to tower 3, and then the smallest disk goes from tower 1 to tower 3. So as you can see, this program does work for the case when the number of disks is 3. The same you can check for 4 and 5 onward. So we are not doing a formal proof because this is not the focus of the course. The important concept that is illustrated to you here is that a fairly sophisticated plan, indeed a plan which has almost 2 power n, where n is a total number of disks, actually there are 2 power n minus 1 moves, is very succinctly, in a very crisp fashion, is specified using a very small recursive function. So observe that this is the whole recursive function. What does this recursive function encode? The recursive function basically encodes the fact that to solve the problem on n disks, somehow move the top n minus 1 disks into the intermediate tower, or rather recursively move the top n minus 1 disks into the intermediate tower by using the destination tower as the intermediate tower, okay? And then move the largest disk which is now available at the top of the source tower to the third tower, which is our destination tower, and then move from the intermediate tower, which is our second tower, to the third tower, again recursively via the tower 1. Right? So this is exactly specified. These are the recursive function calls to move from source to the second tower via the destination tower. And the third one says move whatever has been accumulated in the intermediate tower to the destination tower via the source tower. And these are the well-defined exit criteria for the recursion. Otherwise, the recursion will not terminate. So this more or less finishes the presentation for today. So let us just go back to our slides and observe that we have come to the end of week 1, and it has actually been a very hectic week. We have learned uh, or reviewed very important concepts in this week, and therefore each of you should have a steep learning curve as you go through this week. This is probably the toughest week, and once you understand how to actually implement these in the C programming language, the remaining weeks are going to be the definition of different data structures and then setting up appropriate programs to use them to solve different kinds of problems. Every data structure is useful for a certain kind of a problem. Right? Therefore, understanding the data structure is very important so that you can implement the programs for that appropriate problem. And being able to program, right, in C, right, is the way by which you will really write those programs and feel comfortable and accomplished having learned these data structures. Therefore, this week is very likely to be your toughest week where there are many new concepts which you probably have only studied in textbooks. I'm encouraging you to write programs for all of them. So therefore, you will notice that the programming assignment, the first programming assignment involving recursion, involves binomial coefficients that has been released. And I hope that you are writing down the programs that I have shown you in the lectures, right? At least those, if not more. And today's lecture, you have seen 3 recursive functions for which I have not shown you programs. I encourage you to write recursive functions, right, in C for these 3 particular recursively specified functions, and also run through the code for the towers of Hanoi for 5 disks. Right? So for this, I encourage you to write the towers of Hanoi program in C completely by yourself, exactly the recursive function. Do not Google the code or do not search the internet for the code. Go through the video, try and understand exactly what I have said, the recursive thinking part of it, and try to write the C program with the appropriate exit conditions. That is the best way to learn. Of course, you can choose to cut and paste from an appropriate web page on the internet and compile and run, but that is not the best way of learning. Okay, so thank you very much. That brings us to the end of first week. It has been an eventful week for all of us, and it is also a time when we are understanding all the challenges with uploading the videos and getting the assignments ready on time and so on and so forth. Hopefully, the subsequent weeks will be much smoother, and you will find the course even more enjoyable. I will stop with a very important piece of advice. There is no better way to learn programming than to write programs. So please do not watch this video as you watch a movie or a TV program, right, and go back and read a textbook. Right? So that's the worst way to learn the subject. You will not learn anything. The best way to learn the subject is to get to your computer, sit down, put your fingers on the keyboard, have a notebook by your side, understand the logic, and write programs. After the first time you write a program, it might not even compile. There will be errors. You have to fight through it and make your programs work. Thank you very much for listening to the small piece of advice. Hope you enjoyed this week.